Ready to do this? Spring break wasn't long enough, was it? We're still in the section on improper integrals, so we'll finish that up. You guys ready for the test tomorrow?
No.
Yeah, it's super hard. Like I didn't intend for it to be that hard, but I wrote it and I looked at it and I'm like, oh, this test is so hard. It was crazy. I wrote some of the problems. I'm like, I don't even know if I know how to solve these. This is crazy. And then I was calling up some of my friends, try to scramble to figure out the solutions. But I believe in you guys. I think you guys can do it. Okay.
Isn't the test next week? Yeah.
Well, it was supposed to be, but Kaylee's emailed me and insisted that I keep it till tomorrow. So she sent an email. Her right there. I'm kidding. Of course it's next week. Relax.
Oh, Jesus.
Okay, this one I think we did.
Yeah, we did.
And so that's done. B,
Yeah, we did.
I think we also did B, so this one we also did.
Yeah, we did C.
And we did C. That's done. Okay, so we need to start doing D. Where this went from minus infinity to infinity of that guy. So I'm reusing the same function because integration is not really what I want to teach you guys here. I just want you to actually see in the different situations how you would break the problem up. So we're going to do D and E. Show that this particular integral, 1 to infinity of 1 over x and p dx converges if and only if p is greater than 1, diverges otherwise. Okay. So let's actually get to it. Remember we said, I know it's been a while, so let's just kind of remind ourselves of what this means. This is improper. What does it mean for an integral to be improper, a definite integral? What's the basic gist of it? What's the, yeah?
If A is equal to negative infinity or B is equal to positive infinity.
Okay. Is that the only time we are improper?
Nope.
Okay. What's the other situation?
If the function f of x is undefined at some points on that closed interval, maybe.
Right. So that's basically the idea. Basically the idea is, the gist of it is f does not behave on the interval that we want to integrate on. Right? And so the idea is to use limits to approach the bad points. And in quotations, and not bad, but that's the bad points. The points where we don't behave at, we sort of use limits to approach them and see if the function can give us some sort of approximate answer. Because really, if you just take out a single point, you don't change the area under a curve because the area along a line is 0. And so that's sort of the idea. So sometimes, even though the function does not behave in the strictest sense, it might not be continuous or it might do something crazy, sometimes the area under the curve interpretation still applies because it's not bad enough to kind of get rid of that whole thing we set up with Riemann sums. And so that's sort of the idea. So once we say, and if we get an answer using these limits, we say the function converges to that number. The integral converges to L. So that's just the language that we use. Otherwise, we say it diverges. And diverges in this case includes infinity. So limit does not exist or is infinite. So in either one of these cases, we say it diverges. It does not give us a meaningful answer. Okay. So that's the basic gist of it, right? So we identify a problem as improper if our function does not behave on the intervals. If one of our intervals are infinite, then obviously your function doesn't behave because you can't plug in infinity into a function. Or it might be some finite number where you can't plug into the function there. So you kind of use limits to approach these points. And then if it works out, we say it converges to this number. We can still find an area and have that be meaningful. And if it doesn't, we say it diverges. Yes?
A quick question about point 2. What happens if it's not defined on A or B? Like on the open interval?
If it's not defined.
Because like it says the closed interval, so that means.
Yeah, meaning at the endpoints could be a problem.
Oh, sorry, closed to endpoint 2.
Yeah, closed means it includes the endpoints.
Okay.
Right, so that was, for example, this guy.
Okay.
Right, 0 was here, but I can't plug in x equals 0. And so that was a problem.
Okay.
So it could be at the endpoints or even some point in between could be an issue. So that was just kind of just a reminder about the concept here. But in terms of applications, how you would apply execution, how you'd apply this concept, for the most part, you just replace the bad points with variables and let those variables approach limits, but you kind of do integration as you usually would, so you remember all your integration techniques from before, and then you apply limits at the end, so you have to remember all your limit techniques, including L'Hopital's rule, and then at the end of the day, if you get an answer, that's the answer. If you don't, you say it diverges. Okay. So let's actually pick up where we left off with D. And one other principle that we covered is we really only want to work with one bad point per integral. So if you have something like that, what are the issues here? And so clearly this is improper, since our A is negative infinity, and our B is positive infinity, and there's one other issue. What is that issue?
It's not defined at x equals.
It's not defined on 0, and 0 is inside this interval. Right, so 0 is something that's inside that interval, and our function doesn't work there. So we actually have 3 bad points here. Right, there's the negative infinity, there's the infinity, and there is 0. So you want to kind of split this integral up where you can isolate these 3 bad points so that only one of them appear on any given interval. And so how do you think of doing that here?
You could do like negative infinity to -1.
Okay, so you want to avoid 0, so you can pick something over here, say -1, and so that's one of your guys that you integrate over. So that means negative infinity is one of the bad points, and then what?
-1 to 0.
Then that guy?
And then you have to do like 0 to 1 or something like that. Yeah.
And then that. So it turns out here, to break it up in the way that will work with our theory, will require us to actually break this guy into 4 integrals, right? To isolate 3 bad points, you'll need 4 integrals. You always need one more integral than the number of bad points there are. So that's the first step. First step is recognizing what the bad points are. So you need to check whether the upper or lower limit are infinities, or and find where the function is undefined and make sure it's not in that interval. But in this case, we have 3 bad points. So what I can do here is to realize that the integral from negative to infinity of 1 over x squared dx, I can think of that as from negative infinity to -1 plus -1 to 0 plus 0 to 1 plus 1 to infinity. So that's the first step. Figuring out what the bad points are. Then break it up so that you can have only one of these bad points on any of these intervals. So I want to expose them and isolate them. Then I'm going to use limits to approach these guys. So now here I'm going to take, say, the limit as n approaches negative infinity from n up to -1 plus the limit. And we're treating all of these as different limits. So this guy is approaching 0 from the left. Plus limit as p approaches 0 from the right. Plus limit as k approaches infinity. And we're going to do with each of these. So we knew what the integral of 1 over x squared was, right? It's -1 over x. So here, this guy is going to be, this is the limit as n approaches minus infinity of -1 over x. And that guy is just going to be, you're repeating this formula pretty much. -1 over x plus -1 over x plus and what do we do here? Well, we've already seen, if we look at this guy, or even this guy, right? Notice that here, if I plug in 0 approaching from the left, what's going to happen to this guy? -1 over x, if the denominator is approaching 0 from the left.
Negative infinity?
It's going to give us negative infinity, which negative times negative, this guy here is going to be infinity, right? And so we also have the idea, we mentioned this last time, is that if one part diverges, everything diverges. We're summing things here. So it doesn't matter if all the others give me a nice behaving number, that one part gave me infinity. So if I add them all up. And so in that case, it's not very meaningful for us. And so we would say the answer here is it diverges. So this is one thing you can realize will happen, or you can apply. The integration itself is going to be the same for everyone because you're literally integrating the same function. The difference is you might be plugging in different limits. But if you can just notice one part of these guys that doesn't behave, right? So you start working out this limit, you'll actually get an answer from working this one out. Then you move on to that one, you realize, oh, that messes up. You don't even have to check the other two, they don't matter. Once you find one guy that doesn't give us an answer, you just say the whole thing diverges. So that diverges. And that was D. Okay, let's move on to E. Any questions on this, by the way? Yeah.
How come it goes to infinity again?
Oh, because I'm plugging in the limit. So here, this one, I would apply the fundamental theorem of calculus, right? So this is, say, the limit as m is approaching 0 from the left of, I plug in the m, minus, which becomes a plus when I apply it, and then I plug in the minus 1, so this is pretty much minus 1. Right? Now when I'm finding that limit, I'm plugging in 0 into the denominator here, that's not going to work. Right? So that guy is going to go off to infinity. I wrote it out when we were doing this example, so you can look back at that work. But that was the idea here. So notice that when I'm taking the limit as I'm approaching 0 here, it's not going to work. What about E? We also won't, I won't give you guys a quiz tomorrow as well, so in the recitation, you guys can either go over the review that I gave you guys with the recitation later, as well as see me during office hours, or if you want to move ahead to get some of the bonus problems, you can do that as well, but I won't give a quiz. So if you have any questions from looking over the review, tomorrow would be a nice time to check it out. We can discuss some things. Yeah, but how would we do this guy? What are the issues here? Yeah? Ahmed?
It's improper because it's undefined at 0.
It's not undefined at 0.
Oh, wait,
Because I have a 1 plus x squared. Where's 1 plus x squared 0?
Never.
Yeah, 1 plus x squared equals 0. That has no solution for real numbered values. Right, so the integral itself, the function itself doesn't give us a problem. Yeah,
It's the positive infinity.
it's the positive infinity that's the problem, right? That's, while 1 over 1 plus x squared will give us a value for any real number I plug in, infinity is not a real number. If I plug in infinity, what does that even mean? So it's an improper integral because of the infinite limit, not because of the fact that the function necessarily misbehaves otherwise. So it's the infinity is the only problem here. So there's really only one point to worry about. So let's say the limit as n approaches infinity of 0 to n of 1 over 1 plus x squared. And you just keep the limit there while you're working out this integral. What is that integral? The integral of 1 over 1 plus x squared.
X minus 1/3.
tan inverse x.
Tan inverse, right? That's something you need to remember. So that's tan inverse of x from 0 to n. So, Sternberg hasn't been a long time, but in terms of math, it's a super long time. You'll be surprised how much you can forget in a week. So make sure you look up all these formulas that we learned before, the main ones that I kind of hinted at are important. So in terms of formulas that will be given to you, I'll give you the formulas for approximate integration. So I'll give you the formula for Simpson's rule, trapezoid rule, and how to find their errors and all of that. But I won't be giving you formulas like integration formulas. So that is something you need to remember. Okay. Yeah. So now I would just apply the fundamental theorem of calculus. Again, I'm keeping this limit here. So I'm waiting until I have this expression. Plug in n, so this is the tan inverse of n, minus plug in 0, so this is the tan inverse of 0. What is tan inverse of 0? Do we know that?
Pi.
So tan inverse of 0, I'm asking if I, when is that true?
Yeah.
It's at 0, x equals 0, right? Remember tan inverse works on the interval minus pi over 2 to pi over 2. So I need to find what angle in that value when I take the tangent of it, it gives me 0. 0 is the value, okay? You can also remember, and this is another important thing to remember, by the way, in general, that the tan inverse graph looks like that. Right, in terms of inverse trig functions, the tan inverse graph is very commonly used in calculus because it is the only one that kind of is continuous on the entire real line. The other inverse tangent functions, they're either confined in a little box, so you can't ask a lot of interesting problems on it, or they have like asymptotes all over the place. So remember, the maximum here is pi over 2, the minimum it will go to is minus pi over 2, and it sort of looks like an S. Okay. So notice that it passes through 0 at 0, so we know that tan inverse of 0 is 0. Okay. And so now basically we end up with this limit. So there comes a point after you apply the fundamental theorem of calculus, it now becomes a limit problem. So you have to remember like how to take limits. And again, all the techniques are permissible here, so you might have to use L'Hopital's rule, something else. So now we end up in this situation. And what's that? It's pi over 2, right? And the main way you'll know that is by knowing the graph. As x goes to infinity, we're asymptotically approaching pi over 2. Right? Another common thing to ask for tan inverse, of course, is as you approach negative infinity. So this is pi over 2, and so it converges. So we can say the integral from 0 to infinity of 1 over 1 plus x squared dx converges to pi over 2. Right? That's the area under the function. Talk about something in general. We'll use this again when we get to series and we're talking about something called the integral test. But for now, I'm just assuming that p is some number, and we're going to prove that this kind of function only converges if your p is strictly greater than 1. So theoretically speaking, this is a very important example. There are a lot of things that we can finesse into looking like this integral. And so knowing about that integral is going to be important. We will look at one application, as I said, later in the series. But it's an important application. In general, 1 over x to the p is undefined if x equals 0, but that's not a concern here. Right? Because 0 is not included. 0 is not included. So that's not the problem. Right? So while this function can be undefined, it's not an issue because we're not at a point where it's undefined. So this function technically will be defined on all points along the interval that we're looking at right here. So the thing that makes this improper is the infinity, or the fact that we want to plug in infinity. Okay. So what we would do here is we'll take the limit as n approaches infinity of the integral from 1 up to n of 1 over x to the p dx. And how do we consider that?
So you
Yeah.
have 1 over, negative 1 over x to the p minus 1. Oh, I suppose that only works for this one.
No.
Yeah, yeah.
Ideas, how do you do that integral? Yeah?
Could be x to the minus p minus 1 over minus p minus 1.
So,
Oh, like, yeah, it has to be x negative then parentheses p minus 1.
so you're thinking of this as the integral of x to the minus p, in other words, and using the power rule.
Mm-hmm.
Okay. And so you would add 1 to the power, divide by the new power, between 1 and n.
Wouldn't you need? No, sorry, never mind.
But only if p is greater than 1 or.
Well, not equal to 1. So remember, there was a gap in the power rule. There was literally one number that didn't work in the power rule. Right? What was that?
1
Is if your p was 1, right? Because then you divide by
or
n minus 1, it wouldn't work. Okay, so if your p is 1, let's say pretend p was 1, what would I have?
just be 1 over x.
It'll just be 1 over x. How do we integrate 1 over x?
ln.
ln. So there are actually two possibilities here. There's the case if our p is not 1, then I would just bring it up and just use the power rule. But in the case that my p is 1, it's just the integral of 1 over x, which I know is going to be ln of x. So there are two slight issues to worry about here. P equals 1 was a kind of weird point because the power rule doesn't work for n equals minus 1. Okay. So let's deal with these slowly. Let's do the p equals 1 case. So assuming p equals 1, I now have the limit as n approaches infinity of ln of x through 1 and n. So this would mean that I have the limit as n approaches infinity of ln of n minus ln of 1. What's going to happen here? ln of 1 is 0. But if I plug in infinity into an ln, it goes off to infinity, right? So it diverges. Okay, so we know it diverges if p is equal to 1. Okay, so now if my p is not equal to 1, let's deal with that situation. Well, now it becomes the limit as n approaches infinity of x to the minus p plus 1 over minus p plus 1 between 1 and n. If I plug that in, I get n to the minus p plus 1 over minus p plus 1 minus 1 over minus p plus 1. Okay, and how do I deal with that?
negative infinity.
Yeah?
Let's just say, the first part, because you have infinity to negative power, so it's gonna go to 0.
How do you know it's a negative power?
I guess it could be.
Literally all I know here is p is a constant. Right? Is minus p plus 1 always negative? No, because if I say p equals a half, it's not negative. So there's another issue to worry about here. Okay? So now, again, we have two cases. As you pointed out, if the power is negative, we don't actually have an issue. We look at the power of n. This is minus p plus 1. So we have case 1, where this guy here is negative, in which case that means that our p is bigger than 1. And what would happen there is that if you take the limit as n goes to infinity of n to the minus p plus 1 over minus p plus 1 minus 1, what would happen is I plug in infinity to a negative power, this part is going to go to 0. Right? And so what I have now is just, it gives me a limit, which is now we already know that p is not 1 because we dealt with that case. So this actually gives us a number. So it converges. And when did it converge? Under the assumption that my p is bigger than 1. Okay? Looking at case 2, what if it were a positive power? If minus p plus 1 was actually positive, this means that my p is less than 1. Then that would mean that my limit as n approaches infinity of n to the minus p plus 1 over minus p plus 1 minus 1 over minus p plus 1. This guy now will go off to infinity, so it will diverge. So we end up with the following 3 cases. It diverges if my p is equal to 1, because that gives me an ln and that goes off to infinity. It diverges if my p is less than 1 because I'm getting infinity to a positive power. This is the only time where it will actually give us a meaningful answer, if my p is greater than 1. So, i.e., this integral converges only for p greater than 1. So we can use that. And this is something that we will be using. So this now, it can kind of be a fact that you just know now. If it's good enough to just be something that you should know. I won't really ask you to derive it ever, but it's something that's important to know. So now is going to be an important follow-up to the idea of improper integrals. We're going to look at something called the Comparison Theorem. And the idea behind this is sometimes f of x is complicated enough so that we can't compute the integral of f of x dx. Right, so example of something like that, for example, would be, say I was doing 1 to infinity of e to the x squared. I mentioned this before, that that's actually something that we do not know how to integrate. I can't get to a formula for that. There is no formula in terms of the functions that we have in calculus, where if you differentiate that formula, you get e to the x squared. Right, that's something that's impossible to integrate, quite literally. Okay, so there's no formula for that to happen. So that kind of throws a wrench in what we've been doing, because how we would deal with things normally in improper integrals is we just take a limit to replace the bad point, we integrate as usual, we get an answer, then we take the limit to see if the limit works. But what if I can't actually integrate the thing that's there, right? That gives us another problem. However, there are times, and whenever this occurs, we can always approximate the answer to any degree of accuracy we want. But sometimes knowing that looking for such an approximation is viable is going to be important. Sometimes we can know whether such improper integrals converge by comparing them. To known integrals. Hence you get what's called the comparison theorem. And there's an analog of this in the series as well, so this is an idea that we will come back to. So it's a very important theorem. At first, me writing it down, the idea might seem a little bit confusing, but really it's a very intuitive idea. So the theorem goes something like this. I'm just going to sort of weigh it not to consider the integrals from of g of x dx and f of x dx. Right, so I have two integrals, they're improper, they have very similar intervals. We're looking at the same intervals, okay? Where, let's pretend that they share this relationship. G of x is always less than or equal to f of x. So I'm looking at two integrals, they have similar limits, but the thing is, on a point-wise basis, I know that this function is always giving me higher y values than that function, okay? What that means is, this would mean that this must be less than or equal to that. Now, and there's a theorem in the book that says this as well, but for now I think the idea is clear enough. If one function is always higher than another function, right? So if that's my f, and then this is my g, and my f is always bigger than my g, then the area under the f must always be bigger than the area under the g on the same interval, right? That kind of clear, okay? And there's an actual theorem that proves this, but I'm just throwing that idea out there. So what this means is the following. From this we can make some conclusions. If the integral of g of x dx diverges, then Oh, there was one other thing here. And f, g are positive functions. I mean, they're always giving a y value that's positive. So I know if these guys exist, there will be some positive number. Can you make any conclusions about this integral if this guy diverges? Yeah?
Integral from a to infinity of f of x will diverge
It
too.
will also diverge. Also, conversely, well, almost conversely, if your f of x converges, then the integral of g of x must also converge. And this is the comparison theorem. I can talk about whether an integral will converge or diverge, not by knowing about that integral itself, but by knowing about some other integral that I can know the relationship between them. So the idea is these will both be outputting some sort of positive number because they're positive functions. And so if this guy has a value, right, let's say I calculated this and it was 2. It means that this integral has to be less than 2. It has to converge somewhere at a point that is either 2 or less. It will never go off to infinity. It won't be able to go off to infinity if it's bounded by 2. So if I know my f converges, it automatically means that g converges. Conversely speaking, if this guy blows up to infinity, there's no way that guy could converge to a finite number because he always has to be bigger than that guy. So if this guy goes off to infinity, that guy also goes off to infinity. So knowing this relationship and knowing what one of the integrals are doing, I can talk about what the other integral is doing in these two cases. It turns out if this guy converges, I can't say anything. This guy could be infinity, he could not be. I don't know. If this guy diverges, again, I can't say anything about that. But in these two particular cases, I can talk about it. If this guy diverges, I know that also diverges. And if this guy converges, I know that also converges. This gives us the comparison theorem. So what that allows us to do is it allows us to talk about the convergence of an integral, not by doing that integral specifically, but by looking at some other integral that I can compare it to in a very predictable way. So, all right, let's look at one example here. Well, I have more examples, but we'll wrap it up with this one. Look at this example. Integral from 0 to infinity of this guy, the cosine squared of x over 1 plus x squared. Now I'm going to save you the trouble here. That has no antiderivative. I cannot integrate. Like if I didn't put limits on this thing and find the integral of that, can't do it. Okay. There is no function that you can differentiate that will give you that as the answer. Okay. But let's say I want to know whether this converges or diverges, right? Converges or diverges, right? So for some reason I'm in a situation where knowing the value of that integral is probably important, but I realize it's an improper integral. I also realize that I don't know how to integrate it. So now I'm like, there might be an answer out there, but there might not be. Should I search for one? And I can know that ahead of time by using the comparison theorem. One thing you can recall here is that there is a bound on the cosine function, right? What do I know about the values, the output values, in terms of magnitudes of a cosine squared?
It won't be greater than 1.
It will never be greater than 1. This will always give me values that are less than or equal to 1. So I know that this guy is a positive function because I'm squaring something, so it's always going to be greater than or equal to 0. But it also never gets bigger than 1. So what that means is that if I look at this guy from from 0 to infinity of cosine squared x over 1 plus x squared, this will always be less than or equal to if I replace the cosine with 1. Right? The area under this will always be larger than the area under that. Right? But what do I know about this? Right. That was the guy we computed last time. We actually know this has an answer. It went to pi over 2. So this converged, right? And this guy converges. So the area under this curve is always smaller than that value, but I know this value is pi over 2, which means the area under this has to be somewhere between 0 and pi over 2. I can't tell you what the exact answer is at the moment, but I know the answer has to be out there. And so it's worth studying further and moving on. So this means the integral of this guy, I can say it converges by the comparison theorem. So the idea is, if you have an improper integral that you don't really know how to actually compute it using the techniques we have, if you have a suspicion that it converges, what you need to do is find an integral that you know converges that you can put above it all the time for all x values, right? If you have suspicions that it might diverge, what you would do is find an integral that's less than or equal to it that you know diverges, right? And in either of those cases, as long as these integrals are positive, you can use the comparison theorem to talk about it. So because this is always less than or equal to that, and I know they're always greater than or equal to 0, it forces this guy to converge whenever that guy converges. So we don't know what this value actually is. We can approximate it, but at least I know there's a value out there that's worth looking into. We'll stop there. We'll do a few more examples on this next time, and we will start. We're supposed to do work, then arc length, but I'll probably do arc length first because it's a much shorter topic, and we can probably get it done a lot quicker.
Is homework 7.8 due tomorrow?
What's 7 point?
Improper intervals.
No, we have more examples.